Welcome back. So this is lecture 49 in this course on Bayesian modeling. The topic of this lecture is cross-validation. In the previous lecture, we built a measure of predictive accuracy of a model. What was that measure? Expected log predictive density of a model. So we learned that how we can compute expected log predictive density of a model, which is a measure of predictive accuracy of a model, right? Now, although you have a measure of predictive accuracy of a model, right, you still need to figure out how actually you are going to compute it, right, and how exactly you are going to ensure that you are actually calculating predictive accuracy on some future data, not on some old data, right, on some future unseen data, right. That's an important point, because one of the interesting thing, interesting situation we are often in, that we have access to some data. So let's say you have some empirical data which has these data points y1, y2, y3, y4, yn. So let's say you have data which has these n data points y1 to yn, right? Now how would you compute ELPD of the model? Well, one approach is this. What was the formula of ELPD? ELPD was expected log. So let's say Q is the model for which we want to calculate ELPD. So expected log Q of yi given, oh sorry, let me write it again, y new I given y obj, where y new I given y obj. So this predictive density of y new I given y obj comes from expected predictive density of each new data point y new I conditional on samples from the posterior distribution which is estimated using y obj, right. This is how we compute ELPD. Okay, but let's say you collect some data in an experiment and these are your data points. Given these data, can you calculate expected log predictive density of your model? So let's say you assume some regression model. So let's say yi comes from normal mu I sigma, where mu I equals to alpha plus beta into some factor xi, right. So it could be any model, could be a very simple regression model. That's not the point, right. So let's say you want to calculate predictive accuracy of your model, and this is the formula you have for ELPD. Okay, so how would you compute ELPD of your model? The problem here is that in the formula itself you have two kind of data, y new and y obs. Okay, but in this particular case you have access to only this single data set, which is the data that you just collected for your experiment, right. Is it y obs or y new? Well, what people do in this sort of situation, basically they do work with this, right. So one of the thing people do when they are in this situation, they will treat this same data as y new as well as y obs. Okay, it's the same data y1 to yn. Okay, what does that mean? That you train your model on this data y1 to n. Basically you estimate the posterior distribution of theta using this data y1 to n, right. So then you will be able to get these samples from the posterior, and then you calculate predictive accuracy of the model, you calculate ELPD using the same data y1 to n. So the same data is used to estimate model parameters as well as to calculate expected log predictive density. What we are doing here essentially is that we are using the same data to train the model and to test the model. Okay, and this is very problematic because this is overfitting. Because when you train the model to this data y obs, whatever y1 to n, right, the model will learn regular features of the data as well as some irregular features of the data. So the model is always going to be really good at predicting this data y1 to n, but it may terribly fail when it comes to predicting some real actual future data. So let's say you plan to run this experiment again in future, and then you would want the model to predict the data. The model might terribly fail if it was overfitted to this data. Okay, so this is called overfitting. So if you use the same data to train the model, by training the model you mean estimating posterior distribution, right? If you use the same data to train the model and same data to test the predictive accuracy of the model, then this will give you overfitting, right? So this is problematic. Then how do we deal with this problem? Well, one absolute solution to this problem is that you train the model on this data. Okay, so by the way, you can also use terminology like y test and y train, okay, because that's more appropriate terminology, right? So rather than using y neo, y obs, okay, you can also use y test and y train, right? This is more transparent terminology. This is training data, this is test data. Okay, so this is terminology from machine learning literature, right? So in machine learning they use test data and training data separately. Okay, so another approach is this, that, well, whatever data you have collected so far, I will treat this data only as my training data. So I will use this only to estimate model parameters, but I won't use this to calculate ELPD. So this test data has to be different. It has to be some future data. So what I will do instead, I will replicate this experiment. I will do this experiment again. Okay, so when you do this experiment again, then you will have some new data. Okay, this will become your y test. So basically some new future data, which has, let's say, data point 1 to, let's say, m. Okay, so this is your new data if you replicate the experiment, or could have same data points as well. Okay, so in this case you are actually doing two experiments, one to train your model and then another experiment to test the predictive accuracy of your model, right? But we practically don't do this. This is what we should be doing if we want to calculate ELPD, but practically we don't do it, right? We do not really test the model on future data. This is an ideal situation. We should be doing this, by the way, but we don't do this. What we have in reality is just this data, the data that you have already collected from your experiment y1 to n. This is the only data you have. Now you want to evaluate the model given only this data, right? So how do we do this, right? So there are some solutions people have proposed around this. So if you use the same data to train the model and test the model, then this would be overfitting. So this would be problematic. Okay, so now you need to solve the overfitting problem. So how do we solve the overfitting problem? So overfitting is training and testing the model using same data. When your test data and training data is same, using same data. But this overfitting problem needs to be solved if we just want to keep using the same data and we do not want to do any future experiment. The question arises that how do we solve overfitting, or how do we manage this overfitting problem? You cannot absolutely solve this, but you need to manage this so that the model is whatever output we get, it's not a consequence of overfitting, right? So one approach is this, that panelize a more complex model, and this stems from the idea that overfitting is actually a problem that happens when the model is more complex or when the model has more number of parameters. What happens when the model has more number of parameters? So, let us say a linear regression with 10 predictors or so. What happens is that as the number of parameters increases, the model starts learning from the noise in the data. So, model starts learning irregular features of the data, right. So, a simple model with one parameter wouldn't learn too much from the data. It would learn only, let us say, certain regular features which might also appear in future data. But if your model is very complex, then it would try to learn almost everything in the data. So, even the noise, right. So, these more complex models are more prone to overfitting. They will have more overfitting problem because they are also learning from the noisiness and irregular features of the data, and when they are put to test against some actual future data, they would fail, right. So, that is the idea. So, we want to penalize more complex models because they are likely to overfit, right. So, that is approach 1. So, we penalize more complex models. How do we penalize? So, let us say subtract the number of parameters in the model from its expected log predictive density. So, we will calculate ELPD using the same data as training data and test data, and then we will subtract the number of parameters in the model from this ELPD. So, we are penalizing the ELPD of the model for its complexity or the number of parameters, right. So, the measure looks something like this, that you calculate ELPD. So, basically it is an estimate of ELPD minus K. K is the number of parameters in the model. So, this is one of the measure, right. This I think is called AIC. Okay. So, these are actually information criterion. So, different information criterion measures, right. And they both use actually similar approaches like AIC, BIC, WAIC. So, BIC would do the same, ELPD, okay, minus. So, this is using the same data as training data and test data minus number of effective parameters. Effective parameters is a similar concept, but we just want to, so it is a more complex measure of like more sophisticated measure of model complexity, right. Similarly, WAIC, which is again subtracts number of effective parameters, but with a different measure of number of effective parameters, right. Another crucial thing about these criteria is that they do not really use a posterior distribution. They do not use posterior predictions, right. So, for example, AIC does not use posterior predictions. It actually computes this ELPD component using just a maximum likelihood estimate of theta. So, idea would be to obtain a maximum likelihood estimate of theta using this training data, and then using that MLE of theta, you calculate basically this term, log predictive density of the model. Similarly, BIC uses maximum posterior estimate. So, basically in the posterior distribution, the estimate you get the value of theta at which you get maximum posterior density, right. So, these measures are not exactly Bayesian because they are not using uncertainty contained in the parameter estimate, right. WAIC I think uses the uncertainty contained in the parameter estimation. You can take a look at these measures in my lecture notes, so you can practice them as well. So, I have written down some code in the lecture notes which you can use to practice how to calculate AIC, BIC and WAIC, right. But this is only one way to solve overfitting problem. So, in all these methods what we are doing is penalizing a more complex model. There is a second method which is this, that well, you have just this data y1 to n. How about I do not train the model on all these data points, rather I train the model only on a portion of data points, and let us call it y train, and then I use the remaining data points as the test data. What it ensures is that it trains the model on a portion of data, so that becomes your training data, and then the remaining portion becomes some unseen future data for your model, because your model is not trained on this part of the data. So, this becomes unseen future data for your model, and this becomes the training data, right. This approach is called cross validation. So, this is the second method which we use, and this is actually the method that we should be using, right, because we have seen the problem with AIC, BIC, WAIC, that they all allow overfitting. They are just trying to penalize the model for its complexity, right. So, this is not a very good solution. This would give you a very rough approximation, right. Cross validation is a much better solution, especially when you have good enough number of data points, right. So, the general approach is this, that we split our data into training set. Okay, so let's say this is Y train and test set. So, let's say Y test. Now, you train the model on this data, basically estimate posterior distribution of theta using this Y train and compute ELPD of the model using Y test, right. So, ELPD using Y test, okay, like this, log of likelihood of Y test I given theta j, right. And this thing we do for multiple iterations. So, in this case we have used this, let's say, first 80% of the data points as the train data, right. In the next iteration we will use, let's say, some other portion as train data. So, let's say this portion will be used as train data. Okay. So, for example, let's say you have 10 data points, y1, y2, y3 and y10. Okay. So, in the first iteration, so you can run a loop for k in 1 to 10. Okay. You run a loop, and what you will do in each loop, that your training data would be, so first time your training data would be y k to, let's say, sorry, so your test data would be, let's say, y test is y k and y train is actually y minus k, that is all data points except this data point y k. Okay. And you keep doing this for 10 iterations. So, every time your test data is changing and your training data is changing. Okay. So, you do this in 10 iterations, right. This is actually, you can decide yourself that how many folds do you want. In this case, we split the training data and test data in basically 10 different ways, right. But you can decide to do it for 6 different ways, or let's say 20 different ways. Okay. 10 is a standard value that is used, right. Not a standard but conventional value. It's useful. There are some results that 10-fold cross validation is good, right. So, that's why this method is also called k-fold cross validation. Okay, k-fold cross validation, because you split the data into training set and test set k number of times. So, in k number of ways, you split the data into training set and test set, right. So, you will have k number of different training sets and k number of different test sets. So, you are actually evaluating predictive accuracy of the model k times, and then you can take a composite measure, the overall, the summation of models ELPD across these k number of folds, right. So, in each fold your training data and test data might look like this. So, let's say this is first fold. Okay. So, in first fold, let's say your y test is y1 and y train is y2 to 10, right. In the second fold, let's say y test is y2 and y train is y1 and y3 to 10. Similarly, in the third fold, the test data is y3 and training data is y1 to 2 and 4 to 10, okay, and so on, right. So this is how these folds will look like, and for each of these fold you will fit the model on this, right, and then you will test the predictive accuracy of the model on this. So you'll get 10 ELPD values, right. So ELPD of the model for fold 1, ELPD for fold 2, ELPD for 3, because there are 10 test sets, right. In a way we have split it into 10 test sets, right. ELPD 4 and ELPD 10, right. So this is for model 1, right. So for a model Q, so this is, so the overall ELPD of a model Q can be calculated as summation of all these ELPDs, right. Similarly, you can also calculate a standard error of ELPD of this model Q, okay. So you can calculate, for example, a standard error of summation of random variables, right? Okay. So for example, a standard deviation of all these ELPDs, right? So ST ELPD divided by a square root of 10. So that would be standard error of ELPD of this particular model, right? This standard error is important because what it tells you is that because the model has, because you have splitted the data into multiple test sets, it could be the case that the model is really good at predicting, let's say 6 test set, but it is really bad at predicting remaining 4 test sets, right. If that is the case, then there is then model is not doing really good. So overall ELPD might be really high, but still there is large standard error. So there is variability in how well the model can predict this data, right. So if a standard error is large, then it could be the case that models are not distinguishable. So this could happen. So for example, let's say there were two models, you have Q and model R, and this is the ELPD value that you have calculated, total ELPD value are calculated using k-fold cross validation for model Q. So let's say this is ELPD for model Q and this is ELPD for model R, okay. So it seems that model Q is better than model R, but it might be the case that the standard error is quite big for model Q as well as model R. So in this case, the models won't be distinguishable if standard errors are large, because what it means is that, well, there is variability in the data, and although the model is doing good in explaining one portion of the data, it is not doing very good in explaining the other portion of the data. So given that, although numerically model Q is better than model R, but you cannot really distinguish between their performance because their standard error in of predicting the test data is actually quite large, right. So you won't be able to distinguish between model Q and R, right. So this can happen, okay. So standard error is really important here, okay. So this is how you can do k-fold cross validation. So what has happened in this approach is that you have solved the overfitting problem by splitting your single data set into multiple folds, into training set and test set, right. And you do it iteratively for 10-15 times, so that different data points become training set and test set in each iteration, right. What it ensures is that you are never using the same data to train the model and to test the model. So your training set is always different and your test set is always different. Another thing it ensures is that um, that you're testing the predictive accuracy of the model on actually each portion of data, not just on one portion of data, but on each portion of data, because we are going through iteration, and in each iteration the test set is changing. So we are taking a different portion of data as test data. So that also allows us to measure how much uncertainty is there in predicting future data, in predicting unseen data by this model, right? So if the model is really good, then that uncertainty wouldn't be that large, right? But by the way, that uncertainty could be large also because if data is noisy, if you have fewer data points, then it could also be large, right? So and that would play a role in model comparison. If your data is noisy, then you cannot be certain that which model is a better model, right? So that's why it is always good to have lot of data points and less noisy data, right? So this is an approach that we are going to use for Bayesian model comparison. Okay, so now you can think, let's say you had two regression models, one which, let's say for reading time data, you have one linear regression which looks like this. RTI comes from log normal mu I sigma, where mu I equals to alpha plus beta into some predictor xi. So let's say this is your model 1 and your model 2 is RTI normal mu I sigma, where mu I equals to alpha dash plus beta. Now these will be different parameters into xi. Okay. So let's say you want to compare these two models. You can compare these two models using cross validation. How we will do it? Well, we will have to estimate these parameters alpha and beta using trained data. So basically, you will first split your data set into training set and test set, and then you will estimate alpha and beta for this model M1. Okay, so alpha and beta for model M1 using this training data. Okay, and you use this training data also to estimate alpha dash and beta dash of model M2. Okay, so now you have trained both your models on this training data. Now you will calculate ELPD of model M1 using train data, using test data, right? Okay. Similarly, ELPD for M2 using test data, right? And then you can take average of all ELPDs across, let's say 10 folds, right? That's how we do it. Now to fit the model to training data, you can use BRMS, right? No problem in that. So you can use any parameter estimation method you want to use. Only thing we require here is a posterior distribution, right? So our first step in cross validation, so the first step would be to split the data into training set and test set. So basically we first divide the data into training set, test set, and you make 10 such folds, k number of folds of training set and test set, right? That's the first step, that we split the data. Second step is train your models on the training data. Basically estimate posterior distribution of the model parameters on using the training data for both the models, right? So for posterior distribution estimation, you can use BRMS package or you can write your own sampler, whatever you want to do. Okay. Once you have posterior distribution, now you draw samples from the posterior distribution, and using those samples, you calculate predictive density of observing the test data, right? And that is a measure of ELPD, right? Now there is one more variation of k-fold cross validation, and it is called leave one out cross validation. I mean, it is same as k-fold cross validation, but what happens is here is that in each test set you have exactly one data point, right? So let's say if your data has 2000 data points, then one of the data point would be the test set and the remaining all of them will be the training set. So that's why the name leave one out. So leave one of the data point out as the test set and train your model on remaining n minus 1 data points, right? And you do this iteratively for n number of times. So you can imagine that this would take time, right? So if you do leave one out cross validation properly, it would take much more time than k-fold cross validation. In k-fold cross validation, you need to fit the model 10 times. In here, you need to fit the model n minus 1 times, right? but there are some approximations. So what they do is that they train the model only once on all data points, and then they approximately measure how good is the model at predicting the remaining data, using some approximation, right? But that's, I wouldn't recommend that. But that gives you a very some reasonable approximate measure of ELPD using cross validation. Okay, there is a package in R if you want to do leave one out cross validation using some approximation, right? It uses approximation. That package is Lu CV, I think. That's the name of the package. You can take a look, right? But in the next lecture, we are going to implement cross validation in R. So we'll step by step, we will write the code that how we would implement cross validation for a simple example, right? And you can actually learn from that example to do it even for more complex models, right? Because all you need is to estimate model parameters and then use those posterior distributions to calculate ELPDs, right? All right, so I will stop here. In the next lecture, we will do cross validation implementation in R. All right, thank you.